welcome you back again. And let's start with this first hands-on session, which pretends to start applying the concepts that we will be seeing during the summer school lectures. Okay, this is the main objective of these hands-on sessions. Just like for today's sessions, the first one will be an introduction to the framework. Okay, so I noticed that there are many people coming from THIMNE, and I guess that for most of you, at least using GID, maybe not Kratos Multiphysics, but at least GID, will be familiar to you. Okay, but this is just the first step. We need to cover that, and we will do it in a, let's say, in an interesting way, hopefully. Okay. So let me introduce myself once more. My name is Sergio Jimenez. I'm assistant professor at the UPC, and I'm also a researcher here at THIMNE. I started working at THIMNE in 2017, yes, and I became a assistant professor last year, sorry, not last week, last year. But I've been teaching since 2018, so more than eight years from now, so quite a long journey already. Okay, and I've been working using Kratos and GID since then. Okay, and earlier in my master's studies. So here you have my email contact. This is the THIMNE one. If you want to write me, you can do that. If you want, you also can find my UPC email, or if you write my name on Google. Okay, it's easy to contact me, and I will be available to respond all your questions. Maybe not during this week because I will be kind of busy, but later on for sure. And if you want to set a meeting to discuss something, I'm also free to do that. Okay. Then you've survived to this first day of the summer school. Okay. We have some interesting sessions. Some of them are, let's say, the basics, and just giving you an overview of the summer school itself. And now we will start with this hands-on session. And as it's specified here, this is a introduction to Kratos for solid mechanics. So Kratos Multiphysics framework, as we will be seeing, is a multiphysics code that can be used to study not only solids, but also fluids, the interaction between solids and fluids, and many other things. But we will be focusing on this summer school, which is dedicated to solid mechanics, fatigue, and nonlinear behavior, and so on the study of solids. Okay. So I will be the responsible to coordinate these hands-on sessions, the three of them. Okay. But apart from myself, there will be some other professors and PhD candidates and so that collaborate with in my group that will help you during this process. Okay. So if you have any question, you can just write it on the chat. Just raise your hand, and someone will respond to you. Okay. So this is the structure for this first session. Let me do something at this point, which is copying and pasting this link. This link here is to download this presentation, not the complete one, because I'm not including the results of the exercises, but you can download the presentation. And in this first hands-on session, I'm also including the PDF containing the information to download GID, install it, and so. So just in case you have not done it previously. Okay. For those who are here and want the presentation, I can then share with you a QR, or maybe send it to you, because I'm not sure if you are connected to the meeting. Then we can sort it out later, maybe. Okay, so let's continue. So this is the structure. I will first of all talk a little bit about the structure for these hands-on sessions, not only for this one, but for these three hands-on sessions. and see which is the purpose of these sessions. Then I will introduce you the GID software as well as the Kratos Multiphysics code from the point of view of the problem type that is inside the GID software. And then we will start talking about the examples for today's class, okay? And the structure for the future sessions will be more or less the same. I will introduce you first of all and review some of the main concepts related with the nonlinearity that we will be tackling during the session, and then we will be preparing and solving some examples, okay? So this is the idea of the hands-on session. During the seminars, the lectures, in the morning, we will be introducing the ingredients that are necessary to then study the specific problem. Alejandro has mentioned, or has introduced you the concept of finite element method. This means that in the elastic problem, some basis for the nonlinear problem, but this allows us already to start with this study from the finite element method point of view within a software, right? So we are moving from these theoretical classes to the simulation. What we need to perform this, to being able to run the simulation? Well, the first thing that we need to know is how to build this finite element model, okay, using the GID software in this case. Then, of course, apart from being able to create the model, then you need to know how to retrieve, how to obtain and visualize the results in an interactive way, but also if you're interested to obtain values for a specific node in your mesh, I will also let you know how to do that. And then, as part of this process, which is even maybe more important, is to have this critical understanding of what you're doing, and then being able to validate the result that you're obtaining. Okay, I'm obtaining colors. They look really, really nice, but is this real? Or this makes sense or not? Okay, so this is the purpose. So today we will be building your first model in using GID and then run it using Kratos. Tomorrow we will move to reproducing a real tensile test. So I will give you experimental information, which is basically what happens when you're collaborating with experimental guys. They will provide you experimental information, and now do whatever you consider, which is basically calibrating a finite element model, right? So we will work on that tomorrow. And then on Wednesday, we will be doing more or less the same, but for the high cycle fatigue model. I will give you once more experimental data, and I will tell you, okay, do whatever you want, which is calibrate the model and then using it to run whatever simulation that you want. Okay, this is the idea. Of course, we will arrive up to a certain point. The time is limited. These concepts and using these models is not easy, at least for the high cycle fatigue and also for the damage model, but we will try our best, and the world doesn't end by the end of this summer school. Okay, so you have plenty of time to continue using and working on these topics. So now let's talk about GID and Kratos Multiphysics. This is the document that I sent you 1 week ago. Some of you received it a few days ago, which is basically the way to install Kratos, okay? I hope that all of you have done that and that everything worked properly, because I have received no message, so I hope it's fine. But basically, these are the tools that we will be using to run the simulations, okay? And this is something that Alejandro already presented, so I will skip it pretty easy, but I will connect this already with the GID structure. So this is the approach that we follow to prepare and to run a finite element simulation. We start with defining the geometry. We will not run, or we will not work with this nuclear containment building. Okay, we will start with something more basic, but we have solved this using GID and not Kratos. We used PLCD, which was another numerical framework, but it can also be run with Kratos. So we will work on building our geometry. Then we will build the numerical model in terms of finite element model. okay, which is the element that then will be interpreted by Kratos. So we will be moving from geometry to finite element model. And now I will let you know how to do that. This here is the, let's say, overview of the main tools that you have in GID referred to creating geometries. Okay, it's just an overview. There are many other things that can be done in GID. From my point of view, or what I end up doing is I create my geometry in another software. In the case of it's a more complex geometry. For example, I use AutoCAD to import step files or so. I modify everything in AutoCAD because I think that it's more prepared to do these CAD operations at geometry level. Then I export the geometry into a step or IGS sort of file. And then that I import that on GID. Okay, but GID is also available to prepare geometries. So let's see how it works. This is your GID interface. Okay, let me do something else. Now, this is your GID interface. If everything is fine with respect to the installation process, this button up here should be in green. Okay, this one here should be green. If it's in red, it's because you have not validated or you have not registered your program. Okay, this is not really an issue. This only indicates that you will be only allowed to create certain types of geometries and models with less than 8,000 nodes, if I'm not wrong. Okay, so this is a limitation, but you will be able anyway to do any sort of calculation. So this is the initial interface that you will be that corresponds to GID. In here, you have some shortcuts to create geometries, to visualize the model, to zoom in, to zoom out. This information in here, all these buttons in the left side, are also in the geometry create interface. Okay. So the best thing that we can do is just go to the first exercise and start working on this. Okay. So let me go back to the presentation. Let's go to this first example and let's try to build this geometry, because the first thing that we will be doing is creating a geometry. Okay. This is the first example that we will be running, which is determine the elastic response, displacement, and reactions of a steel cantilever beam with a thickness of 0.1 meters, subjected to uniaxial tensile load corresponding to uniformly distributed load. I'm just focusing at this point at the geometry. Okay, this is just a rectangle with a certain thickness, and that's it. Okay, so now what I will be creating is a rectangle with one side 5 meters and the other one 1 meter. So you go back to GID. If you want, you can do it later. Okay, I will be doing now, and then you will have some time and you can work on the example. You have various ways in which you can do that. You can create, come to here, geometry, create, and you can create points. This means that in here, if this works more or less like in AutoCAD. Okay, you have here the interactive window in which you can click whatever you want, and you will be adding points. Okay, I'm clicking on the screen and I'm adding points in space. There is the option to go down here in the command line and write the specific coordinates for the node. So for example, I can add here 0, 0, and I will be adding node in the coordinate 0, 0. If I want to add, wrong coordinate. Okay, so I can also interact with the command window to provide the corresponding information. Okay. If I don't want to add points and I want to directly create a line, I can come here to the element create line or go to geometry, create line, straight line, and then you can say it appears here a message that says enter points to define the line. So the first point is 0, 0. And I will say join. Well, I will comment this later. And then it's asking me to create the second point. So the second point will be 5, 0. X coordinate 5, Y coordinate 0. Okay? Then I said that it was 1 meter width, right? So this will be 5, 1 because it's absolute coordinates. Then I go back to 1, 0. And then, sorry. Let me just erase everything because you can create like this your geometry. Okay, this is an alternative. You can, for this sort of simple geometries, you can also go to this button here, which allows you to create predefined geometries. And for example, here you have the rectangle. So you can click on that rectangle, click wherever you want on the screen, and build your rectangle. It will directly create the corresponding entity. Okay, so this is another option. In GID, the button that confirms an action is the escape button. Okay, so it's not enter, it's escape. You can read it here. Okay, in the command line it says enter first corner point or escape to leave. So I don't want to do anything else. I click escape and then I'm leaving this process. Okay, it's not enter, it's escape. Okay, then there is a difference between this rectangle that I created here, entering point by point, and the upper one, which is this pink internal rectangle. Do you know what's this? It's a surface. There is a difference between this rectangle here and this one here. We are creating entities. I start from the point, from node, then I move to line. There is another entity which is the surface, which basically defines a region closed by lines, and there is another entity, which is the volume, which is a region closed by surfaces. Okay. In GID, this is indicated with a color code. Points are these dark blue elements shown on screen. The lines are the light blue elements. The surfaces are these pink regions, and then the volumes are lighter blue. Okay. Just because I've used this element here, this create object, I'm already creating the lines together with the surface. There are various visualization modes in GID. This is the element type of visualization, which is set here as normal. Okay. If I click here, I will be switching from various types of visualization options. We can move to the flat, which depending on the light direction, you will see here the surface itself. Now you can notice that this is indeed a surface, while these here are just lines. Okay, but let's go back to the other one. So now, if I want to convert this closed region, which are just lines and points, into a surface, what I should be doing is coming here to geometry, create, and the corresponding the surface, which is this NURBS surface. Okay, there is the same button is down here, and what you can do here is do it by selecting the corresponding lines. So let me just select the 4 lines which create the surface. I click on escape to confirm the operation, and then the surface is created by in automatic way. Okay, now this is already a surface that is a region closed by lines. Okay, the same can be done in an automatic manner. Let me erase the surface. The same can be done in an automatic way by coming here to create NURBS surface, and it says automatic. And I click on automatic, and it is asking me, enter the number of lines. And I will tell him, okay, every region, every closed region formed by 4 lines, I want to create a surface. So I write here 4, enter, and this should create the corresponding surface. This is really useful in the case that you have many closed regions, okay? So this is done in an automatic way instead of just clicking on all the lines. There is a button here. I will not go into the 3D for today, so I will not create now the volume. But what I will tell you now is this other button here that I've already used that, which is the delete button. In here, you have put the possibility to delete various types of entities. There is a hierarchy while using this operation. Okay, you cannot delete a lower entity if it's connected to a superior entity. For example, in this case, I cannot delete the line without deleting the surface, because the existence of the surface depends on the existence of the line. Okay, so I cannot delete the line without deleting the surface. So if that's the case, I can click on here also lower entities. This means that if I delete, it kind of connects all the elements. I want to delete everything in here, so I click on all types. I select all the elements that should be deleted. I click escape, and that's it. Okay. So this is my geometry. This is just the geometry. Nodes, lines, surfaces, and volumes. Okay. There are many operations that can be done to this element here. But I think that we will not be using them today, so maybe I can show them tomorrow. Okay. But these operations, let's say advanced operations, are here in the utilities. Okay. So you can have a look, and you have the presentation with the details for that. So we are at this point. Now we can create the finite element mesh. These or the instructions to create this finite element mesh are detailed in this button here. Okay. By default, the GID is proposing you a mesh based on triangles and a structure type of mesh. This is, I will be able to mesh mainly whatever kind of surface that you provide me. And this can be checked just by clicking on generate mesh. If I do so, here it's giving you a parameter to control the mean size of that element. I will use, or let me use the value that is provided by default, click OK, and then GID does some operation, and now I click on view mesh, and this is the mesh that I obtain. This is done in an automatic way, okay, without clicking on anything, just generate mesh. And these are the default parameters. Now, if I want to change any parameter about the definition of this mesh, what I need to do is affecting or specifying which are these parameters. The first one, changing the mesh criteria for the size. So I go once more to the generate mesh. It will appear this button here, and instead of 0.25, let me use 0.02. Click on OK, and then the mesh will be regenerated. And basically what I'm saying is, now I want thinner elements, smaller elements. So this is my new mesh. Okay, if I zoom in, these are triangles and structure triangles. Okay, they are kind of randomly positioned inside the structure. This here is not anymore a geometry. This is a finite element mesh. There are no nodes, there are no points, no lines, no surfaces. These are elements. Okay, these are elements. What if I want to use a structure mesh or other type of element? Then I go here, I click on, for example, the element type, and instead of triangles, I can use quadrilaterals. I click on quadrilaterals, and then if you see here in the command line, it says, enter surfaces to assign this element type. Surfaces. So I click on my surface, this rectangle here, it's selected, I click escape, and then the mesh criteria for this surface is set to quadrilaterals. Now, if I regenerate the mesh, I should obtain quadrilaterals. Okay, let's do that. This is the new mesh. And instead of having triangles, what I have are rectangles, quadrilaterals. okay? But the structure or the way in which this is built is still unstructured. If you want to obtain a structure type kind of mesh, you should come here to mesh, structure, and then define a criteria to create this structure kind of mesh. Okay, for example, you can specify the amount of elements that you want at a certain line. So I click here. It's asking me, okay, select the surface at which you want to apply this kind of criteria. I select my surface, click escape, and now it's asking me, how many divisions do you want for this element? So for example, let me write 10, assign, I select the line. This line conditions the opposite line because structure meshes can only be applied to surfaces that have 4 sides, okay? I click escape, and then for the other line, I would say 50. Click escape, this condition has been set to the line. I click once more escape to confirm my operation, and now I can regenerate the mesh. If I do so, I should obtain quadrilaterals and structure. Let's see. This value here is not anymore being used because I have already specified the criteria for the size, which is based on amount of divisions. So this number here will not affect the result. Okay, I click OK, and I'm obtaining this new mesh. And this is a structure mesh made of quadrilaterals. Okay, so at this point, you know how to create a geometry, basic one, straight lines, points, surfaces, and so, and how to move from this geometry towards the finite element mesh. This is only GID. I have not used Kratos. This is just GID. And then, once you have the finite element mesh, you import the calculator, which is Kratos, okay, or whatever other problem type that you want to use. Okay, there are many research groups here at TIMNE that use GID as preprocessor. So this is generating the mesh, generating the geometry, generating the mesh, and then having an interface with their corresponding calculator, okay, which inside of GID is named problem type, okay? So this is basically this point here, calculating something, okay? In our case, we will be using Kratos, but if you have a look at the list of problem types, you will see that GID can interpret, can understand input files from ANSYS, if I'm not wrong, from PLCD, from many other softwares, okay? And this is basically the interface corresponding to Kratos. How do we arrive to that point? If you click on data, you have here a button that says problem type, and if you have retrieved the model of Kratos, which was something that was described on that document that I shared with you, Kratos, now Kratos will open in the GID framework, in the GID environment, okay? This is Kratos. This is the initial window that, that corresponds to Kratos. In here, we will be selecting which type of problem we will be solving from that point on, okay? It can be thermal problem, structural problem, fluid structure interaction, etc. Okay, yes? You should retrieve the model of Kratos. Have you done it? It will, if I'm not wrong, what it should open, it's like a problem type of Abacus that allows you to generate the input files that then will be read by Abacus. So it's not that you will be able to run Abacus. What you will be able to do is creating the input files for Abacus. So in here, just because we will be, we are interested in studying solid mechanics, we click on structural, okay? The structural is the application in Kratos that has been created to, or it's devoted to study solids. So I click on structural, and now it's asking me which type of problem will you be solving. For today's session, a 2D kind of problem, okay? So I click on 2D, and then a new window has opened here. This is Kratos inside GID. Okay, and this is everything that you can do in Kratos from the GID. Kratos is not only this. Okay, I will show you tomorrow a comparative between what can be done from the problem type inside GID and what can be done from a developer perspective. So downloading Kratos in a full mode, let's say. Okay, but this is Kratos. So here, basically, in order to create our model, our structural model, which means applying boundary conditions, applying the material properties, defining which are the loads that will be applied to our material, defining the solution strategy, etc., etc., etc. This is basically creating the problem to be solved. Everything will be done from this window here. And basically, we will be going from the top and just complete all to the bottom and complete all the parts here. Okay, but let me continue with the presentation and then I go back to this. So this is the structure to create the problem, and then we will be viewing results. Okay, this is basically the visualization of the results. We will see that after we create the model. Okay, so at this point, we can continue with the examples. So this was the example. At this point, we have created the geometry, which is basically what is defined here. You create the points, move to lines, to surfaces, and volumes if necessary. This is the tool that I will be mentioning tomorrow, which is move and copy, that allows you to perform other operations, useful operations. Now we have opened this structural 2D. Okay, so you have here all the steps that we followed. And we now need to convert this geometry into a model, okay, into the problem that we want to solve. So let's see this here. While we are introducing these features, these characteristics in our model, we need to ensure that we are working with the geometry. We don't want to introduce these parameters at the mesh, but at the geometry. Why? Because if we introduce all the information that we will be defining now at the mesh and we regenerate the mesh, we will lose all the information. Okay, so we need to go back to the geometry view, which basically is pressing this button here, toggle geometry mesh view. We have not lost the mesh. Okay, it's here, but we are now on the geometry view. And now let's go from the top to the bottom. Let's start with the model information. Here, what you can see is the type of problem that you will be solving. By default, it's set as non-linear, even though we will be solving today a linear elastic problem, but you can leave it like this. This static kind of problem is allowing you to define which sort of problem will you be solving. For today, we will stay with the static kind of problem because we only want to obtain results for a constant load. But tomorrow we will start with the quasi-static kind of cases to see which is the evolution over time of the response of a certain material. Okay. So for today, we leave it as it is, static and non-linear, and we move to these parts. These parts is the block in which we will be defining the material properties and assigning those material properties to the corresponding element. Okay, so we click on solid because we are generating a solid element, not a beam or truss or cable kind of elements. We are working with solids. It's a plate, but it's a solid. And we double click on here and we have now this new environment, which is the one in which we will be defining the type of material and the constitutive law that we will be using for this new part. So, first of all, we select the kind of element. We will be solving a small strain case. So we keep with this element, which is solid small displacement. If you are interested in more advanced kind of elements, you have them available here. Alejandro has worked and has implemented recently well, 1 year ago mainly, this mixed formulation, which was proposed by Professor Cervera and Professor Ecumenti. So it's available also in Kratos. These are for the finite strain, the total Lagrangian kind of element, but we will continue with the small displacement. Okay. Now we select which is the type of constitutive law that we wanna use for our material. As I was saying to you, we will stay with linear elastic. Okay, so we have two options: plane strain or plane stress, as Alejandro has, I think that he has mentioned. In this particular case, in which we are studying a thin plate, so thickness is small compared to the other two dimensions, and so in thickness direction, the stresses are considered as zero, or can be considered as zero. We will be selecting this plane stress kind of constitutive law. Okay, so we select the plane stress. And then the other properties to be selected, the density. I think that nothing has been said about the density here, but I have the numbers in here. The density, it's the same as it is proposed. Then the Young modulus, I set it to 210 gigapascals, so we can change here the number, 210 gigapascals. These are pascals, so 210 to the power of 9. The Poisson, 0.29, so basically the same value, 0.29, 0.29. And the thickness, in here is specified that this steel sheet has 0.1 meter of thickness. So let me switch this to 0.1, and everything has been already defined. Now, this needs to be applied to the corresponding geometrical element that will behave according to these material properties. So I click on select. And GID says, enter surfaces to be assigned to group solid auto 1. So I click on the surface to which I want to apply these material properties, to which I want to assign these material properties. It has already been selected. I click on escape. So it has already been transferred to this element here, and then I can modify the name. For example, steel 1. And I click on OK, and then the group has already been created. Okay. If this has been done in a proper manner, this group should contain the material properties that you have defined. And apart from that, this group that is shown in this left-hand side tree should also appear on this right-hand side tree. Okay, in here, if you click on groups, I have the steel group. And now if I click on this button, I will be visualizing where this group has been assigned. You can see here that it has been applied to this surface here. So everything is fine. I click escape to go out of this visualization mode. And now we continue. No more material properties. If you have more materials, then you should create them and apply them. In this case, there are no more material properties, so we can continue. These time intervals is not that interesting for this problem because we will be just applying a load constant in time. Okay, so this is not important for this case. Then about the initial conditions, this is neither interesting for our case because all the kind of information that we will be introducing can be described from the boundary conditions section. In these boundary conditions, we can apply displacements conditions, so an imposed displacement or just imposing zero displacement for a certain point, line, surface, well, not surfaces because this is 2D. But basically this kind of boundary conditions to your model. And then the other ones are for if in the case that you are running a contact simulation, then you will need to use these other options here. So in this case, I want to apply a boundary condition which corresponds to a fixed n. I double click on displacement, then I select the line, and I want to apply a zero displacement condition to this end here. So this is the in x direction displacement must be zero, and in y direction displacement must be zero. So this is fine. I click on select, I select the line, and once everything is selected, I click escape, and now I name this condition, which is boundary condition 1. click on OK, and everything is done fine. Now, the problem statement says that at this end, I want to apply a certain load, 100 kilonewton per meter load. So I go back down here to the next section, and these are the kind of loads that I can apply to my model. Self-weight, load on points, load on lines, and pressure on lines. In this case, what I want to apply is a load on line, okay? Just to meet what is shown in the statement. So I click on load on line, and these are the options. Here I have the modulus, and here is the orientation, okay? So if you write here 200, in this line here, you will be applying a load with modulus 1 in the direction 200, 0, which is 1, 0, okay? So the modulus of the load must be applied at this line here. If you apply the modulus here, you will retrieve nonsense results because you are not using properly this section here, okay? Or you are not applying properly the load. So we want to apply the 100 kilonewtons, so 100,000 Newton per meter load in the direction x equal to 1, x equal to 1, y 0. Now I click on select, and I apply this load to this line in here. And then load 1, for example. So now my model is the geometry that I created at the beginning contains the information of material properties, boundary conditions, the displacements which are constrained, and also the load condition on this end here, on the right-hand side end. Okay, and everything can be visualized from this panel here. I can visualize the load, imposed load on this side, and I can visualize here the material property and also the boundary condition on the left-hand side. Now, if we continue this solution, there are many options in here. The important ones, echo level, well, not maybe for this simulation, but anyway, you can switch it to 1. And by doing that, basically what you will be doing is telling Kratos that you want to obtain information from the calculation view window, okay, so that you know what's going on during the calculation, in case that there is an iteration process or so. The amount of iterations, this is necessary for the nonlinear kind of problem, not this case. And the usual stiffness in first iteration, and this must be set to yes. Okay, this is something specific for Kratos. If you are interested, then I can do some comments on this. But for the moment, you should set it to yes. That's it. Nothing else in here. Nothing about the parallel configuration. We are not running contact problems, so nothing to change in here. So the only thing missing now is this result section. By default, what you will be obtaining, this is basically telling you which is the information that you will be retrieving as post-process at the element level and at nodes, okay? So from the element, basically what we will be obtaining is just von Mises stresses. And at node, you will be obtaining displacements and reactions. So that's perfect, because basically in the statement, I ask you to compute displacements and reactions. So we can continue like this. And then there are two post-process files that we can obtain using Kratos, which is a GID output, so that can be read later on the GID. And there is also a BTK, which can be later written in ParaView. Okay, so those of you that use ParaView to see your results, you can use the BTK output. Okay, but this is up to you. So nothing else here. Now, before running the simulation, which is the next step, we need to transfer this information that we have introduced at the geometry to the finite element mesh, okay? Because these are two different entities. We created the finite element mesh after creating the geometry. We imposed all the information at the geometry, but now we need to tell the finite element mesh, okay, import this information to the finite element mesh. How do we do that? Regenerating the finite element mesh. So we go back to the mesh, click on generate mesh, click yes. The options that we defined previously will be maintained. So nothing to be checked here. And now this finite element mesh contains the information that I introduced in Kratos. Something that I forgot. You should save, okay? Because save the project, because it can happen that GID close, and then these are not good news. So let me just save this. Now, the problem is prepared. The only thing that I need to do is run the simulation. This can be done from two buttons here. Calculate button and calculate, or the Kratos, and you have two options here. Run, no write, and write, no run. The way in which we will be running the simulations will be using this button here, okay? Because for the nonlinear problems, we will modify the input files and then just run it. So it's better that you get familiar with this way to proceed. So now we need to create the Kratos files to then run the simulation, okay? Basically, if you go to the case that you've created, this one here, these are the files that GID has created. None of these files can be used by Kratos. Kratos use other sort of files, okay? So what I need to tell GID, the first thing that I need to tell to GID is create the input files necessary to run the simulation. So I go back to GID, go to Kratos, write calculation files, no run. And if you see here, it says MDPA and JSON written okay. GID has written the input files for Kratos. So if I go back to my folder, there are 4 new files that have been created. These 4 files are the ones required by Kratos, nothing else, okay? So if you are just running a Kratos case, you do not need any of the other files. You just need these 4 files: MDPA, the main Kratos, the project parameter, and the structural material. Okay, I will show you them tomorrow. Okay, not today. But these are the input files. Now that I have created the input files, I can go back to this button and say, okay, I want you to run and now write the files, because the files have already been created. Now I click there, and the calculation process has started. Okay. Once the calculation process finishes, then you should receive this message here saying, your calculation has finished. What do you want to do? Okay, and stay in the preprocessor space, or move to the post-process. Let's move to the post-process. Here we have the second part of GID, post-process. So we have done the geometry, the finite element mesh using GID. We have created the structural model, let's say, using the Kratos problem type. We have used Kratos to run the simulation, and now we will be using GID to visualize the results. This is the interface for this purpose, okay? Everything looks more or less the same, but this panel, this left-hand side panel, has changed. The buttons now are different. And in here, for example, you have this button that says contour file, and you can click on displacement and X displacement. These are the results the X displacement results that we are obtaining for our model. Okay, and in here you can see the legend for these results. There's the minimum displacement, sorry, the maximum displacement, +1. Okay, and this is the minimum, 0, which corresponds to the fixed end. So it looks like that the simulation has been done in a proper manner. At least it seems like it's done in a proper manner. Okay, the same can be done for the other variables that we've defined as post-process variables: displacement, reactions, and mimesis. Here you can see sorry, not this one. The results obtained as von Mises stresses for the quadrilateral elements. So this is the stress distribution, von Mises for the von Mises measure. Okay, and the same for the reactions. So, and now is where the problem starts for you. What I'm asking you is to verify if these results are correct or not, okay? Which is the last step that is missing, which is verifying that the results are correct, okay? So the question is, how would you do that for this particular case? How would you check that the results are correct? Yes, this is elastic beam, straight beam, simple geometry, and the solution, the analytical solution, is well known. So we can check the analytical solution of the displacement, for example, and compare the displacement that is given by the analytical solution with the corresponding, the one that we obtain here, as well as the reaction. We are imposing an axial force, and here we have the reactions. So if we sum up all the punctual values of this reaction at this end, we should obtain the same value as the load that we've imposed. That load was 100 kilonewton per meter, okay, in thickness. So you can convert this into a punctual load and compare it with the total reaction on this end here. So you can do that, and what you will be obtaining is this here. Let me just show you. This is not included as part of the presentation that is in the link, okay? But this is everything that we've done up to now. These are the results, and the question is, are they correct or not? And this is the expression basically to compute the displacement, the analytical value, okay? And this is the displacement. I'm not sure if I've obtained the same. I should have obtained the same, 2.3 something. Here it is, 2.375, okay? It depends on the finite element mesh that you've used, but the value will oscillate a little bit. And this basically leads to the second question, which is even though the result is pretty close, is this good enough? What would you say? What is a good result in terms of an approximate method, which is basically this finite element method is an approximate methodology.
Depends on the criteria and application that we are designing or solving our problem for.
Okay, but from a numerical perspective, is there any way to say, oh, with this result, mesh convergence? What you can do is start refining the mesh, see when the results that you're obtaining are stable, converge to certain result, and then you do not continue refining it because it would result in more cost. But if you are just getting this value or the one that I get, the first question is, okay, and which one is the good one? The one which is closest to the converged result. So the first thing that you should be doing in this sort of analysis is ensuring that the mesh that you're proposing is good enough in terms of some convergence, some sensitivity test, okay? Now, second example, and I will stop here my explanation. You have half an hour to work on that, okay? This is the second example. Now, instead of doing a tensile test, elastic one, what I'm proposing you to do is a bending test. You have similar kind of structure, it's a cantilever beam, but now instead of applying a linear load on the end, at the end of the sample, what you should take into account is the self-weight of that specimen, and for that element, obtain the displacements and the reactions and compare them against an analytical solution, okay? So now it's time to you to work. I will, for those at home, how many people are connected?
Right now we have 42 people.
Okay, so what I can do for those at home is, what I want to do is split you in two rooms, okay? And each of you will be with Lucia or Aslan. And if you have any question, you can just direct your questions to them, okay? So let me split the session into groups. think it's not like this. Transfer. Okay. You do not have permission. Okay, Aslan, I will give you now permission. Sala de trabajo 1. Sala de trabajo 2. Okay, where are you, Aslan? You can start. You need the link, right, to download the presentation. How can I do that? Let me see if I have... you can join... I will do that. Let me just try to share with you a QR instead of... But I'm not sure if it's available. No. So please join the meeting and I will share the screen again. Not the screen, the message. Okay. Here. Okay, you have permissions, right, Aslan, now?
Yeah, thank you so much.
No worries. So whenever you are in the call, just let me know. I need to maybe give you permissions. Yes. The link. Let me send it to you by Discord, and I will directly send you the link. I'm not sure if this is okay. This is an image, so just give me a second. Now, have you all access to the meeting? Have you had the link? Lucía, no sé si me escuchas. Si en algún momento necesitáis algo, me dices. Y voy a la sala.
Vale.
Gracias. So if you have any practical question on how to use DLD or something, just let me know.
And the presentation, when if I enter after you send the link,
I said it once more.
I don't know if you can link like marcar.
Yeah, I think so. I will do that.
In a message.
Yeah, like this.
Like that, yeah.
Fijar este mensaje. I think. Thank you. I have the results. I mean, yeah, I have the results also for this. For this example, and also I have the Excel analysis, and so on. Okay, I have not mentioned about how to visualize the results. So basically, what I call is just to graphically obtain the results in GID, but there are ways to also obtain the numerical. Okay, so if you want to know how to obtain the numerical values for the displacement, for example, the that's
I think the part I'm missing is the one that you explained about like connecting all these conditions to the nation. I think that you did correctly until the point I was working with the geometry, but then I missed this that part. That's the
it's just regenerating the action, which is not conventional.
okay.
So now you've already transferred the action. And there is a way to check that. Now that you will be creating the files, the Kratos files, you can open one of them and see which is the information that has been transferred. Okay, we can do that. And if you go to the folder,
Which also was a question I had, because I had this folder when I basically saved the project, but I think I'm not getting the files in the same folder. Probably I need to set up a working folder or something.
you cannot change the name of the folder. If you do that, information will be something pretty written and easy
Here I have.
to open it. This is a problem.
Okay.
Yeah, it's kind of tricky. Even though it's .gid, it's a folder.
Yeah.
And if you look, the names inside for all the files, these are already files, have the same name as the folder. And this is something which is necessary.
Is this the same file extension and also format as mesh?
Not
No.
sure. I don't think so. I don't think so that they are compatible. I think that the GID can open mesh information from Gmesh, but I'm not 100% sure.
Okay.
The Gmesh is the open source.
Which one is the one that for this one?
For example, structural materials. No, down there, the last one. The last one. If you open this one is a file containing the material information, material properties information. So here you can see which is the constitutive law that you have assigned in an elastic plane string. Well, we are using plane strings.
Yeah. Need to check. I did all that.
Okay, no worries. And then this is the material information that you have. If you modified something in the GID, then you need to regenerate the file.
Yeah.
This means regenerating the mesh and rewriting the input.
Okay. Okay.
I'm guessing we use the same constitutive properties, right?
If you want to get the same results as myself, yeah.
Yeah.
Otherwise, I mean, you can use whatever you want. I'm just trying to give kind of a realistic vision to the exercise. For example, tomorrow I will provide you real experimental results from a tensile test. So, of course, you can do you can use other data, but if you want.
No, but I mean for the because
For
I'm
the purpose
guessing
of the class, you can do whatever you want.
these are the things that.
Yeah, as in here. Ah, okay, yeah, because I'm not mentioning which are.
No. Para este no, porque no.
Ok. Sí, para aquí puedes usar las mismas propiedades de material. Al final aquí lo interesante es comprobar cuál es la respuesta analítica.
Claro.
Cómo hacer comparativas.
Plane stress, estamos probando.
Plane stress. Yeah, sure. This slide or which one? Okay. Only 29, just like the others. We can use the same properties, but even, I mean, for some year, we're not having each of them. So you can set whatever. But the thing here is that if you change the material properties, you need to ensure that then you update even the geometry, you need to ensure that you update properly the analytical formulation. In this case, you will need the value of the inertia of a square or rectangle section. For those that do not remember that, it's dh to the power of 3 over 12. Okay. This is your section. This is z, this is y, this is x. The inertia that you are looking for is the inertia in y with respect to the y-axis, which is v times h to the power of 3 over 1. This is v, and this is h. In order to be able to apply boundary conditions, you first need to apply the introduce the material. So it's in parts. But before doing that, move to the geometry a bit. Because this is the you need to click here. So in the geometry view, now you will be introducing all the properties. So now, once you're in here, you will that's a solid. This is the first step to be done. Click on that, and now you will introduce the material properties. And once you've created the material, then you can introduce the load and the boundary condition. So it's kind of you need to really follow the steps, otherwise it gets crazy. Now, The surface. In this case, the surface. If it's a 3D model, then you should create the model. In this case, it's a 2D case, you should apply it. Yeah. And then click on escape or end. In this case, it's y is -1. You have the this coordinate system. So basically, what it's telling you is that you will be applying a modulus, which by default is the beta of the gravity, which then will be multiplied by the density that you are specifying to reveal. It's done automatically. Because otherwise it's saying like you're saying that you're imposing a force in the surface. Which is the modulus, and then you specify which is the orientation. You can switch the orientation of the gravity to whatever direction.
Like make this up with.
Yeah.
Oh, okay.
No, you are in the finite element view. So you need first to switch to the geometry view, and once you are in the geometry view, you need to switch. Now by doing that, you are now in the geometry. And now you can do it, but you need to get out from this environment. No, if I can, you can do that, but then finish with this, and I will sort something because one of the process maybe has not properly been created, and it may create some conflicts. So assign the corresponding boundary condition, and then just we have it. Actually, if I don't know, it's already created. Here, this is the part in which the groups, the acids that you create using this boundary condition, material properties, nodes, and so on, are and here, you can do is just double check that everything in here coincides with the information that you really want to know. For example, the first element here is displacement autobahn, which indeed does not appear. And this one maybe is the one that you've started creating, but you've not ended up creating. So what you should be doing is eliminate it. Click on that. Now let's look for the second one. This is the displacement auto 2, which is basically either here. So this one should go. And let's see what's the third. Click on the click on this button here to come out. Here you can see which is the area in which the boundary condition has been. Now if you open this part, you will see here which is the boundary condition of your element. So 0x, 0y displacement, and this one. So this one is the this one is the one that you are working on. The same can be done now for the last one. This one should be the point is you have applied it to the final mesh, right? So you should erase this and create it based on the mesh. So basically, you erase this one. Yes. That's also able to recreate this. Click on solid. The first thing, no. First you need to create this thing there. The part solid. And apply the corresponding material properties, the ones that we want, with the corresponding resistance stress. Now here, there is over 1. Over 1. Okay. And this then select the surface. Because in the previous case you select all the elements, which is not needed anymore. It will work also fine, but this is a surface. You need to select it would work properly it has not been selected.
Y a ustedes se toman los que más quieren tener mejor. Cada vez que pensamos en
Because these are solid. You're still working with the solid. So you need to select the surface.
Yo digo,
So if you select the surface, everything will be selected.
también te debe dejar claro que
Exit, write the name that you want, and click OK.
si sabías todo lo que era la visión. Ya se queda.
No.
Perdón,
Why you select
solo la saber.
the surface? And the surface is the surface containing the lines containing the nodes. As you select in the before, you selected the element, the final element mesh. The problem of selecting the final element mesh is that at some point, you raising the mesh, you will lose the mesh. Toggle between one of them, and you will be seeing that. Now, you need to make sure that this block here is the one in here. So you need to find out which is the one that you want to keep, and the other one's the lead.
Right, usually want this blue be more dense.
It can be switched. If you want to be blue less intense, it's also possible. Basically, here, what you're saying is that this value is greater, so this one is very large. Basically, if you click here, this button is to show you the function. You click here, the displacement, and here you can see the differential at the bottom. Yeah, it looks fine. This is basically what I want to tell you. Here, apart from visualizing it, you go here. Show you the function. Okay, so these are the values. This is the minimum value, maximum displacement or minimum displacement in the code. This is the value that should be compared with Now you should look for the analytical equation to compute the maximum displacement in a cantilever beam, which is subjected to a uniform distributed load, which is basically the same way, and compare the two And for the movement and the reaction, it's a little bit more tricky.
Pero sería algo más o menos como esto, ¿no?
Esto es el desplazamiento,
Nuestras zonas de acción.
las reacciones. Vale. O sea, al final lo que tendrías que encontrar
Es como compresión, tensión.
that's it. So basically what you will end up having, the model itself in Kratos knows nothing about movements. What you will be obtaining is a force distributed in length, and you will have a force in this direction, okay, or in opposite direction, repeat, this direction. You will have values at all the nodes of your final element mesh, and you will also have values into this direction. X and Y components of the reaction. Okay? The point is that in the case of the Y, basically the sum of all these punctual forces must be in equilibrium with the summation of all these vertical forces, because the equilibrium must be satisfied in vertical, horizontal direction, and also for moment. Okay, so you should be comparing this force with this reaction, and both must be equal if you are satisfying equilibrium conditions. Okay, and apart from that, this here, what you end up having is this kind of situation. So basically what you should obtain is this sort of force distribution. And you can, from this load distribution, you can compute the corresponding moment. because these are punctual forces at a certain distance from the center. So you can compute the moment associated to each punctual force. Okay? If you do that, you can obtain something like this. This is the distribution of vertical reactions, and this is the distribution of horizontal reactions. Horizontal and vertical. Okay? And then you can compare this against the analytical solution, which is basically the situation. Okay?
¿Cómo se hace and how do you link the cuts in order to get the or how do you
How do I obtain this? Yeah, let me explain that. In Kratos, in GID, and maybe I can let me just cerrar grupos. Okay, let me explain something about how to build this sort of, or how to obtain this sort of solution, okay? Which is the description of the horizontal and vertical reaction at a specific section. If you go to your model, and let me open here the corresponding simulation, if I'm not wrong, is this one here. If we open this post-process file, this is basically the reactions. For example, in X direction. Okay, these are the reactions that we have obtained. So there is an option here that says list some filter results. You click on here, and then it tells you, okay, what kind of variable do you wanna obtain, or which kind of variable you wanna report? Nodal variable or elemental variable? If I click on elements, then von Mises will be allowed, will be a variable that can be selected. If you click on nodes, then the kind of variables that can be obtained are the displacements or the reactions. So I want nodes and reactions, and then I click on select. And now I can select the nodes from which I want to obtain the certain variable. So I select the nodes in this end here, and once I have selected them, I click escape, and I obtain this list here. This corresponds to the X, Y, and Z reactions for each of the points. So I can take these values, go to an Excel file, and open them. Let me show you which is the result that you should be obtaining if you do so. This is the exercise bending. So these are the reactions in X direction, in Y direction, if I'm not wrong, in X and Y. Is this correct or not? Y, moment. Yes, I think so. These are the X. These are the X. Yes. So, sorry, no. This is the position of the node. This is the position of the node. Because I wanted to draw this chart here. Okay. So this here is the reaction that I should have obtained from that analysis. Okay. Here you have the various points from 1 to 7. Okay, if I selected them properly. 1, 3, 4. Okay, so basically you can obtain the information from this tool in GID, and you can end up drawing this sort of charts. Okay.
Okay, is that drawn on Excel or?
I've drawn them in Excel, but these are to superpose images. Okay. No, you cannot create a 3D.
Yeah,
No.
ya iba a decir.
No, esa función en Excel no existe todavía.
Lo que yo por lo menos hago es que me voy a la misma herramienta que te permite graficar eso.
Yeah, you can do that.
Y le hago un export.
Yeah.
Pero no sabía que se podía hacer de esta manera.
Sí, hay muchas maneras. De hecho, para...
Creo que es un poco más fácil.
Sí. There is another option here in GID, which is basically creating a chart. In this button here, if you click here, you have the possibility to draw charts with some specific criteria. For example, the one that you can use here is the second option, which is creating a chart that will contain the value or the progression of a certain variable throughout a line. So in here, for the axis direction, you will see line variation of that variable. Okay, so variation along a line. And then for the y-axis, I want to plot the x reaction. So I click here. Now I select the line along which I want to get this result. Okay, and this is the solution that I get for that line, along that line. Okay, in this case, for some reason, I only have three nodes
Es
here.
que yo creo que es un poco, pero tú puedes
Puede ser.
definirlo manualmente.
Yeah. Okay, but you can work in that way. Okay. So it's 4 p.m. It's up to you if you want to stay more or if you want to leave. Okay, I can stay here half an hour more if you want to keep working. But we can close the session, today's session for the summer school, because we've been here since 9 a.m. So let's close the session for today. See you tomorrow at 9 a.m. again. Okay. Have a nice afternoon. Bye-bye.